So you'll be using this sort of as a on again, off again kind of additional support type thing for the for the unit. So basically today, our job today is to derive the fat equals MAV equation. F delta T is equal to M delta V. I call it fat equals MAV. Technically, it's called the impulse momentum equation. And so we're going to drive that. We're going to solve problems using it. And basically, you're going to understand how it relates to everyday life. And in fact, we already saw it in the video with the vehicles. And I'll relate that back to that shortly. So with that handout for yesterday, 7.2, impulse changes momentum. If the momentum of an object changes, either the mass or the velocity or both change. If the mass remains unchanged, as is most often the case, then the velocity changes and acceleration occurs. What produces acceleration? We know that the answer is force. The greater the force acting on an object, the greater its change in velocity, and hence the greater its change in momentum. How long the force acts is also important. Apply a brief force to a stalled automobile, and you produce a change in its momentum. Apply the same force over an extended period of time, and you produce a greater change in the automobile's momentum. A force sustained for a long time produces more change in momentum than does the same force applied briefly. So both the force and the time are important in change in momentum. The quantity force multiplied by time interval is called impulse. So this part of the equation, the F delta T part, is called impulse. And unfortunately, the letter that we use for impulse, I believe, is the capital J. They don't use I because I stands for current, so electricity. Even though J is for joules, right? But as a unit, it's J. So impulse is F delta T. The greater the impulse exerted on something, the greater will be the change in its momentum. And the exact relationship is impulse equals change in momentum, which is the second half of the equation. The impulse, F delta T, is M delta V. And because momentum is mass times velocity, change in momentum is the mass, which does not change, multiplied by delta V, which is what this is here. So the impulse, F delta T, is equal to the change in momentum, which is mass times the change in velocity, or fat equals mass, because the little deltas look like 8. Convenient. The impulse-momentum relationship helps us to analyze a variety of situations where the momentum changes. Consider the familiar examples of impulse in the following cases of increasing and decreasing momentum. So, increasing momentum, case number 1. To increase the momentum of an object, it makes sense to apply the greatest force possible for as long as possible. For example, for teeing off and a baseball player trying for a home run, do both of these things when they swing as hard as possible and follow through with their swing. Big news. All right, so if you play any sport where you swing something, whether it be a golf club or a baseball bat or a tennis racket or just about anything where you're swinging something, right? If I'm swinging that baseball bat, they always tell you to do what? Follow through. Why do they do that? And there's a scientific reason for it. You're going to have no power. That's what, a lot of the coaches don't understand the physics of it. They just know that if you someone sort of half swing, if you sort of do like this, right? You don't get the same power. You want to follow through. Okay? And why is that? Well, when you follow through, let's go back to this equation here. When you follow through, okay? If I'm hitting a baseball, does the mass of the baseball change? No. If I follow through, what I do is I increase the length of time that the bat is in contact with the ball. Right? If I apply the same force, same size force, but I increase my delta T because the mass of the baseball doesn't change, to make the right-hand side of the equation equal to the left-hand side of the equation, the delta V must also increase. And an increase in delta V means you change the velocity by a whole lot more, which means the ball goes farther, faster. Okay.
Theoretically, if you stop for that very second the ball left, though. That would make a difference.
Correct. But in that follow through, you actually are, I mean, we're talking very, very brief differences in time, but significantly enough to make that change in velocity. I mean, if you double the length of time, then this doubles. It has to. Okay? And a double here is very small, but a double here can be large. Right? So you're right. Once the ball has left the bat, there's no point in following through. Right? But it's that mental thing about thinking about following through. What does it do? It increases that brief contact time. Okay? Same thing with golf. Same thing with tennis. Same thing with just about everything. Now the reverse is true as well. In the car crash situation that you saw in the video, how does that apply to this? The change in velocity has to be the same. If you're driving your car at 100, it's got to go to 0, right? To stop. So the delta V is the same. The mass of the car doesn't change, so the right-hand side of the equation doesn't change, right? How do you then reduce the force? Increasing the time, right? If these things on the right-hand side are the same, and I increase my time significantly, then what does that do? It decreases the force, which is good if you're a person riding in a car. Would you rather have a small force exerted on you over a long period of time, or would you rather have a large force exerted on you for a short period of time? Most people would choose the first one. Small force, long period of time, right? I went over here to Anderson, and I push on him with, say, 50 newtons for, 20 minutes. It'd be annoying and awkward, but he'd rather that than me whack him very quickly. Well, okay, that's the idea. So increasing momentum. And if you read there the case one, that's what they're talking about there. To increase the momentum of an object, it makes sense to apply the greatest force possible for as long as possible. A golfer teeing off and a baseball player trying for a home run do both of these things when they swing as hard as possible and follow through with their swing. The forces involved in the impulses usually vary from instant to instant. For example, a golf club that strikes a golf ball exerts zero force on the ball until it comes in contact with it. Then the force increases rapidly as the ball becomes distorted. The force then diminishes as the ball comes up to speed and returns to its original shape. So when we speak of such impact forces in this chapter, we mean the average force of impact. Be careful to distinguish between impact and impulse. Impact refers to a force and is measured in newtons. Impulse is impact force times time and is measured in newton seconds. So back to that idea of impulse. It's measured in not newtons per second, newton seconds. Case 2, decreasing momentum. And you can just look at the pages there. Basically, I've explained all this already. If you were in a car that was out of control and had to choose between hitting a concrete wall and a haystack, you wouldn't have to call on your knowledge of physics to make your mind. Common sense tells you to choose the haystack. But knowing the physics helps you understand why hitting a soft object is entirely different from hitting a hard one. In the case of hitting either the wall or the haystack and coming to a stop, your momentum is decreased by the same impulse. The same impulse does not mean the same amount of force or the same amount of time. Rather, it means the same product of force and time. By hitting the haystack instead of the wall, you extend the impact time, the time during which your momentum is dropped to zero. A longer impact time reduces the force of the impact and decreases the resulting deceleration. For example, if the time of impact is extended 100 times, the force of impact is reduced 100 times. Whenever we wish the force of impact to be small, we extend the time of impact. We know that a padded dashboard in a car is safer than a rigid metal one, and airbags save lives. That's why we put airbags in. What does an airbag do? It increases the amount of time that force is applied to you, right? If you just smack into the steering wheel, right, the time is very short. If you smack into the airbag, it slows your face down before you hit the steering wheel. That's what the idea of the airbag is. And there's the picture there with the haystack, and you can see the big S and the small V's and so on, right? Explains it all there. Okay? Same idea here on the right-hand side. Jumping from an elevated position down to the ground, what would happen if you kept your legs stiff and straight instead of bending your knees? Bending your knees, you increase the amount of time, decrease the force. Okay? If you're boxing and the guy whacks you, you are supposed to ride the punch or give with it, right? And as you do that, you increase the amount of time. All the same exact. Well, flip the next page over. The safety net used by circus acrobats is a good example of how to achieve the impulse needed for a safe landing. The safety net reduces the impact force on a fallen acrobat by substantially increasing the time interval of impact. Sometimes the difference in impact time is important, even if you can't notice it given a surface. For example, a wooden floor and a concrete floor might seem rigid, but the wooden floor can have enough give to make quite a difference in the forces that these two surfaces exert. Okay? The reverse is also true. 7.3, or bouncing. If a flower pot falls from a shelf onto your head, you may be in trouble. If it bounces from your head, you may be in more serious trouble. Why? Because impulses are greater when an object bounces. The impulse required to bring an object to a stop and then to throw it back again is greater than the impulse required merely to bring the object to a stop. Suppose, for example, that you catch the falling pot with your hands. You provide an impulse to reduce its momentum to 0. If you throw the pot upward again, you have to provide additional impulse. It takes a greater impulse to catch the pot and throw it back than to merely catch it. This increased amount of impulse is supplied by your head if the pot bounces back. That's not good. The fact that impulses are greater when bouncing takes place was used with great success during the California gold rush. The water wheels used in gold mining operations were not very effective. A man named Lester A. Pelton saw that the problem had to do with the flat paddles on the water wheel. You've seen the water wheels on boats, I'm sure. Maybe not live, but certainly in TV or movies. He designed a curved-shaped paddle that caused the incoming water to make a U-turn upon impact with the paddle. Because the water bounced, the impulse exerted on the water wheel was increased. Pelton patented his idea and probably made more money from his invention, the Pelton wheel, than any of the gold miners earned. Physics can indeed make you rich. And there is I think there's a picture on the next page, isn't it? Of the Pelton wheel. If I throw an egg at Joey, and he goes to catch it, how should he catch it? Put his hands up like this and close his eyes? Only if you want to laugh at him. What should he do? Catch it, and then do what? And cushion it, ride that catch, right? Or a water balloon. Same idea. Why do you do that? What is that catching a water balloon and sort of going with it? Do for you. Decreases the force by increasing the time. You all know this, you just don't know that you know it. Okay, so as I said earlier, we will derive the impulse momentum equation from Newton's second law. It's the easiest derivation you'll ever see. We'll relate the impulse momentum equation to real life situations. I've done that already. Baseball bats, tennis rackets, car crashes, getting punched in the face, blow darts, all of those are relating it to real life situation, and then we're going to be solving problems right away. Okay, this is just basically a quick review about momentum. You can choose to write it down or not, here's your choice. Consider the following examples. A car and a train are traveling at the same speed. It would require more force to stop the train than the car. Why? More mass. The train is much more massive. A bullet fired from a gun penetrates a woodblock much more than a bullet of identical mass thrown by hand. How come? More velocity, right? It's equal partnership here, the mass and the velocity. Both relate to the momentum. Okay? These two cases result of momentum. Momentum is the product of the mass of a moving body and its velocity, or P equals mv. And if you haven't gotten that already, you should certainly jot that down or at least commit it to memory. You've seen this already. A bar, average acceleration, is equal to delta v over delta t. Okay? Newton's second law also states that F equals ma. And so you take this version of A and you plug it in there. And in fact, the guy in the video said that Newton's first law, or Newton's second law, was actually this one here. And we've sort of stepped it back to this. But substituting A in there for A, delta V over delta T, gives us F equals M delta V over delta T. And then all I've done here is we've rearranged that to this. F delta T is equal to M delta V. And that, my friends, is the derivation for the impulse momentum equation. All you have to do is write this and substitute the A in there and get that, and then rewrite it as that. go back to that because it looked like some people were jotting it down. This is commonly written as the F delta T is equal to M delta V, impulse momentum equation. The product of a force and the time interval during which it acts is called the impulse. That's the fat part, the F delta T. Can also be referred to as the change in momentum. That's the M delta V, the math part. Okay, and remember that impulse, oops, is sometimes referred to as J. Since the change in momentum depends on the force and the time that the force acts, this has some use in sports. Anytime you are following through, baseball, tennis, golf, blow darts, okay? Increasing the time increases the change in velocity. That's why they tell you to follow through. Even throwing the ball, yeah. Yeah, same thing, right? You're increasing. If you just throw and then stop real quick, which some little kids do, right? They think they're throwing it faster. It actually puts a lot of damage on their arm, right? Because they're decelerating so fast, right? If you follow through, you're increasing the amount of force. The good pitchers, you see them, they're falling right through. They're like, almost like touching the ground, kind of, right? Yes, same thing. Even volleyball, swinging at a spike, same idea. Okay, so here's a couple sample questions. The problems are actually quite easy. It shouldn't cause you any problem at all. What force will give a 1 kilogram mass a velocity of 4 meters per second in 3 seconds? This is the mass. This is the velocity. This is the time. You're asked to find the force. Solve for force. The change in time is 3 seconds. The mass is 1, and the change in velocity, it goes from rest, goes from 0 to 4. The delta V is 4, right? That's pretty easy. Those are the kind of questions you might expect to see in a multiple choice format, right? Because they're pretty simple. A 10 Newton force acts on a 2 kilogram mass for 5 seconds. Find the impulse, find the delta P, and find the final velocity of it. Because this is generally more what people are interested in, is finding out how fast something's going. I'm going to let you try that one. So the impulse, you would write J is equal to F delta T. So that would just simply be 10 times 5. So the impulse is 15 Newton seconds. The delta P, the change in momentum, is the same as the impulse. Okay, now what are the units for delta P? Momentum is mass times velocity, kilograms and meters per second. So it's actually over here, it's actually 50 kilogram meters per second. A Newton second is equivalent to a kilogram meter per second. And now find the final velocity object. Let's see. Delta P is equal to M delta V. 50, the mass is 2. Delta V, 25 meters per second. Does that make sense? I think when you see it, you go, okay, yeah, that's easy, right? Again, it's the how do I write it down that's the hard part, right? Yeah. And that just comes from practice and experience and confidence. Last one. I'll give you a chance to write it down, then we'll have a look. You can try it if you like to. How much time will it take to slow a 5 kilogram body moving at 20 meters per second to 5 meters per second if a braking force of 10 newtons is applied? Be careful here. What's the one difference? It is slowing down. I guess that's one difference. I guess there's two, right? It's slowing down, and there's 2 velocities given in the question, right? So the delta V you have to figure out first. Okay, let's have a look at this here. First thing to realize is you've got to find that delta phi, right? It's going from 20 to 5, so the change in velocity is 5 minus 20. The velocity change is by minus 15, right? Now plug it into the FAD equals MAV, or the impulse momentum equation. How much time will it take? We're solving for t. The force is 10. 10t, 5 times minus 15. So t is 5 times minus 15 all over 10. It's going to be minus 7.5 newtons. Am I right? Did I do that right? Oh, time. Yes, minus 7.5 seconds. Can it be minus 7.5 seconds? No. What's going on here? The force should be negative 10, exactly. It's a braking force. The force should be negative 10, which is going to make that negative, which is going to make your time positive. Did I make that mistake on purpose? I didn't actually, but it worked out quite nicely, didn't it? Because it would be a common mistake that you might make. So, you'd likely get 2 marks for that simply because of having to do that step. I think you're in good shape. You've got a worksheet there in front of you that says impulse and momentum. Little reminder in the top right-hand corner, impulse equals force times time. You should be okay, I think, with all of those. Answers are on the back, and there's solutions as well as the scan code. So, enjoy.